Yeah, and so while ProClass is a cluster-based approach, we will have an instance-based approach with PrDeCon. Well, the basic idea is the same as in ProClass, but it uses a different cluster model. Actually, the cluster model of DBScan, the density-based cluster model. And in that case, as you may recall, so k-means, k-medoid cluster model, it is, you have the medoids or the centroids, so the cluster representatives, and you always work with clusters and refine them. In DBScan, you work with points and densities around points, and then collect points along those density connected chains and stuff like that. So in DBScan, you have a much more point-centric view, or the algorithm at least has a much more point-centric view. So it makes sense probably to now also look for the subspace preference of points instead of clusters. Yeah. So PrDeCon does exactly like this. So it uses DBScan, but actually a special DBScan, not a special DBScan, but a special distance function between points that adopts the subspace preference of the points. Yeah, and it takes two additional parameters to the density parameters, epsilon and min PDS, which is delta and kappa. Kappa should be much larger than 1. And then it defines for each point a so-called subspace preference vector, WP, of this point P. And it defines it like this. So if the variance along a feature in the epsilon neighborhood of the point is smaller than, or in that case greater than this delta, then it is set to 1, the preference vector. And if it's smaller than the delta, it's set to kappa. So what does it mean? Well, if you take a look at this image here, so you have the point and the epsilon neighborhood. The epsilon neighborhood is computed in the full dimensional space. Yeah? And now, if you look at the variance along each of the feature, you say, okay, if the variance is large, you set the preference vector to 1. And if the variance is small, you set it to kappa, which is much greater than 1, or should be much greater than 1. Yeah, so the preference vector is actually a d-dimensional vector, and each feature is weighted. So the non-interesting points or not so interesting features are weighted by 1, and the interesting features having a small variance are weighted much higher. Yeah, so that is the idea basically. So in that case, in this example, the feature AJ will be weighted by kappa, and this one here will be weighted by 1, AI. Yeah. So this is basically the idea, and you do that for each point. So each point gets its individual preference vector, which indicates the subspace preference of this point. Yeah. And this is computed by analyzing the feature-wise variance of the epsilon neighborhood of P. Okay, what do you do with that? Well, you use that as a weighting factor for the distance function. So the distance from P to Q with respect to P, you just use the Euclidean distance or the weighted Euclidean distance, and you use the subspace preference vector of P for this weighting. Yeah? And obviously, this is now not symmetric anymore because Q may have a different weighting vector. So the distance from P to Q with respect to P is different than with respect to Q. Yeah? So if you set the weighting vector of Q in here, it might be a different value. And in order to do that, to make that symmetric, because DBScan needs a symmetric distance function, you can use, or you have to make that symmetric, and you just can do that using the maximum between those two preference distance functions. Yeah? So you take the distance between P and Q with respect to the preference vector of P, and the same but with respect to the preference vector of Q, and then just take the maximum of both. You know? Yeah, and if you have defined this distance function, what follows is basically nothing else than running dbScan with this distance function. And there's some kind of syntactical sugar here. So you define the preference epsilon neighborhood of a point using this preference distance, which is basically something like this here. So this is the simple or the original epsilon neighborhood, and the new preference neighborhood comes down to some kind of axis parallel ellipsoid where the variance, where the low variance features are weighted by 1 times k, a kappa, and the others are weighted by 1. Yeah, so the high variance, like a2 here, the vector, the weighting is 1, and in the other direction the weighting is kappa. So the visualization is that the epsilon neighborhood is somehow bumped in that case by a factor of kappa. Yeah, so in this direction, a1, you weight all the distances here in the preference vector by kappa, meaning that points that are very close have a much higher distance. Yeah? Okay, so with this preference epsilon neighborhood here, you can of course define preference weighted core points, preference weighted direct density reachability, connectivity, all that stuff we already defined for dbScan originally. And you just use this preference, the symmetric preference weighted distance function. And a subspace preference cluster is then a maximum density connected set of points associated with a certain subspace preference vector, because that is the vector that all those points typically have in common. Yeah? And clusters then may have arbitrary shape in the subspace projection. Yeah? So here in the projection, you can think of some original spherical epsilon neighborhoods that you just, some kind of shift around, because this is the projection of the entire space on this preference, on the subspace preference, so to say. Yeah? So the clusters in the subspace projection may have arbitrary shape now, which is different to a proclus here actually, which ends up in in something which is again spherical in the projections, of course. Yeah? So because it's a partitioning based cluster model. Yeah? Okay. Yeah, and there are some more variants in this projected clustering thing. So DOC is a variant which is actually randomized or random based. Yeah, so it defines clusters as dense hyperrectangles, a little bit similar like clique. Yeah, and in one run it computes at most one cluster, and it uses random sampling for subspace learning. So it basically samples points and computes the hyperrectangle around those points, the minimum bounding hyperrectangle, and then evaluates if those hyperrectangles are small enough or enough points are in those hyperrectangles, and what is the correct projection of those hyperrectangles such that the hyperrectangles are, so to say, small enough, dense enough. Yeah? And then there is another variant I want to mention, which is COSA, which learns a distance matrix that can be used for clustering. So very similar like this one here, PrDeCon, which is, well, this is a kind of distance matrix, in that case a weighting, yeah, and you can also learn this weighting or distance matrix a little bit different, but also COSA, like PrDeCon here, uses instance-based locality assumption. Yeah, so that is the basic limitation for all of the projected clustering algorithms. Well, DOC does not use locality assumption because it uses random sampling, but COSA and PrDeCon learn this subspace preference of points. So the weighting vector or the distance matrix for adopting the distances, they learn that from the local neighborhood of points in the entire feature space. Yeah, so look at this once again. In order to get the subspace preference vector here of P, we evaluate the epsilon neighborhood in the entire feature space. Yeah? And the same here for Proclus, where we use the locality of the medoids in the full dimensional space. Yeah? In the full dimensional space, in order to see is there some kind of preference, subspace preference in the locality of the medoid, meaning that there is some that there are some features with a low variance and some features with high variance. So that is the basic downside of all those methods, the locality assumption. Yeah? Okay, so that was projected clustering, and we will have another podcast starting with pattern-based clustering coming up. See you there.